Here's an exponential equation that might look intimidating at first. We've got this variable x showing up in two different exponents with two different bases. But the thing is, there's actually some beautiful hidden structure here that we can exploit. The key strategy here is to rewrite everything in terms of a common base. Once we do that, the problem becomes much more transparent. Looking at this, we've got bases of 4 and 2, and you might notice that 4 is just 2 squared, which means we can express everything in terms of base 2. Since 4 equals 2 squared, let's make that substitution. Now, everything on the left has a common base of 2. Quick reminder about exponent rules. When you raise a power to another power, you multiply the exponents. So, a to the m, all raised to the n, becomes a to the m times n. So we multiply 2 with the quantity x minus 1, which gives us 2 raised to 2 times the quantity x minus 1. Distributing that gives us 2x minus 2 in the exponent. Now here's another useful fact. Subtraction in an exponent is the same as division. A to the m minus n equals a to the m divided by a to the n. Let's use that to rewrite the left side. So this becomes 2 to the 2x divided by 2 squared, and we can simplify that denominator right away. 2 squared is 4. Now here's where it gets interesting. Look at this numerator, 2 to the 2x. We can use that power rule in reverse. 2 to the 2x is the same as 2 to the x, all squared. And this is the crucial observation that unlocks everything. What we have here is actually a quadratic equation in disguise. The exponential structure is hiding a polynomial pattern. Notice that the term 2 to the x appears twice, once as a squared term and once as a linear term. To make this quadratic structure explicit, let's use a substitution. We'll set a new variable, y, equal to 2 to the x. With y representing 2 to the power of x, our equation transforms into something much more familiar, a standard quadratic. To solve for y, let's first clear this denominator by multiplying both sides by 4. This leaves y squared on the left and 4 times the quantity y plus 8 on the right. Distributing the 4 gives us 4y plus 32. To solve a quadratic, we need to set it equal to 0. Let's move everything to the left side. This gives us the standard quadratic form. Y squared minus 4y minus 32 equals 0. Now we can factor this. We need two numbers that multiply to negative 32 and add to negative 4. Those numbers are negative 8 and positive 4. So we can write this in factored form. From the factored form, we get two possible solutions for y, either y equals 8 or y equals negative 4. We've solved for our temporary variable y, but remember the original problem was in terms of x, so we need to substitute back. Replacing y with 2 to the x gives us two possible equations. Let's think about the second equation. Can 2 to the power of x ever equal a negative number? Let's visualize the function y equals 2 to the x. The graph of 2 to the x, shown in green, is always above the x-axis. It never enters the negative region, so it can never equal negative 4. So this case gives us no real solutions, which leaves us with only one valid equation. 2 to the x equals 8. We can express 8 as a power of 2. 8 is 2 cubed. Since the bases are identical, the exponents must be equal. Therefore, x equals 3. Before we wrap up, let's verify this by plugging our solution back into the original equation. Substituting x equals 3, we get 4 to the power of 3 minus 1 equals 2 cubed plus 8. On the left, 3 minus 1 is 2. On the right, 2 cubed is 8. 4 squared is 16, and 8 plus 8 is 16. Both sides agree, so our solution checks out. And just to see this from another angle, let's verify visually by plotting both sides of the equation. Here's our coordinate plane. The blue curve represents the left side of the equation, and the green curve represents the right side. The solution is the x-coordinate where these two curves intersect. and you can see they intersect at exactly 1 point. The intersection occurs at the point 3, 16. The x-coordinate is 3, which perfectly confirms our algebraic solution. Thanks for watching. If you enjoyed this problem and want to see more, consider liking this video and subscribing to the channel.